So interpretation, A, if you think about it, is exactly the rate at which subproblems proliferate. So let's call it rates of subproblem proliferation. Okay? Just look at the recursion tree, right? Every time you go down a level, a factor A blow up in the number of subproblems. Okay, so that's working against us. Okay? That makes us nervous. On the other hand, B to the D is the rate of work shrinkage per subproblem. Okay? So RWS, I'll call it. So first think you're already familiar with the case where D equals 1. Okay, so that'll be like in merge sort. So what am I saying? I'm saying in merge sort, every time you recurse on that subproblem, we're only going to have to do half as much work as we did in the original call. And that's because we pass it an array of size half the length. And if you plug in 2 to the 1, you get a factor 2. So a factor 2 savings in work per subproblem. Think a little bit about what if B equals 2 and D equals 2. So then B to the D would be 4. So I'm claiming a rate of work shrinkage of a factor 4 as you go from one level to the next. So how would that happen? How would it be that you cut the input in half, but somehow you get a factor 4 savings?
Well, because D was 2, that means each level takes like n squared, so a combination work. And because you cut by 2, that's cutting by a factor of 1/2 twice the square.
Right. So suppose we weren't doing linear work outside of recursive call. Suppose we were doing quadratic work. Then cutting the input in half doesn't just save us a factor 2. It saves us something much bigger. It saves us a factor of 4. Right? So basically, if the running time is n squared, plug in n over 2 into that formula, and you get n squared over 4. Okay? So as D grows large, whatever shrinkage in input you have is actually getting amplified. Okay? And the work shrinkage is even bigger. Conversely, suppose D equals 0. Right? Then no matter what B, so that means you're doing constant extra work each recursive call. And then, of course, it doesn't matter how rapidly you're cutting the input size, you're still going to do constant work per call. Okay, so the bigger D is, you get an amplification of the savings as you shrink the input. As D goes small, gets close to 0, you get sort of less and less. You get diminishing returns from shrinking the input as far as the savings in work. Okay, so it's really not. The key point being, your intuition is probably highly tuned to the D equals 1 case, and you say, oh, the savings comes because the input is smaller. I'm just pointing out there's a subtler effect, which is if you have nonlinear work, then actually B to the D is really the relevant savings. Okay, so it's not just the savings in input length, it's the saving in the number of operations you do, which depends also on how the running time depends on the input length. Okay? So again, forces of evil, A, how rapidly the subproblems are exploding. Forces of good, B to the D, it's how much lazier, how much quicker you can do each input problem at subsequent levels. Okay? So I can now tell you completely why there are these 3 cases, and in 2 of them, it should even be almost obvious or very believable why you get the running times that you get. Okay? So intuition for 3 cases. Depending on which of the 2 sides wins or if there's a draw. So first, suppose there's a draw. Suppose the rates at which subproblems multiply is exactly the same at which the amount of work you have to do per subproblem goes down. Then what can you say about the amount of work you do at each of the levels of these trees? Is it going up as you go down the tree, going down as you go down the tree, or staying the same as you go down the tree? Staying the same. So it's exactly what we saw in merge sort, where we derived a bound of 6n, independent of j. So we had the exact same bound on the work per level, didn't depend on what the level was. That was because in this case, subproblems were doubling, work per subproblem was halving, it canceled out. Okay, so that is what is up with the first case. So same amount of work per level. And if you think about it now, it's obvious what the runtime is. Why? Well, we know how much work we do at level 0. Right? We do n to the d work at level 0, just by definition, by the recurrence. Those log levels, we do the same amount at every one. Clearly, we must be doing n to the d log n work. Right? What else could it be in case 1? All right? So you'd expect n to the d log n when there's a tie. What about the case where the forces of evil are beaten by the forces of good, by which I mean, yeah, problems are proliferating, they're increasing, but the savings per input problem is going down even faster. Okay, so maybe you get twice as many subproblems, but you're doing only a quarter as much of the work on each of those subproblems. Again, think about the recursion tree. Think about going down. Is the amount of work going up or going down in this case, per level? Okay, each level, you do less than the previous one. Okay, yeah, there's more subproblems, but your savings is even greater. Okay, so overall, the work is decreasing for each level of the tree. Less work per level. So which level is going to have the most work? The top one, the root. Okay, so you'd expect, or maybe conjecture, that the root would dominate. You know how much work you do at the root? It's n to the d. So you get in case 2, you get n to the d. Okay? In some sense, given this intuition, the answer is the obvious one. The answer is the one you would expect. All right, so the third case is where we lose the battle. Okay, so we are doing less and less work per subproblem, but subproblems are proliferating so rapidly that rate outpaces our savings. Okay, so now what's happening as we go from the tree top to bottom? What's up with the work per level? So now it's going up, right? So now we do more work each level. So which level is going to dominate? The bottom one, the leaves. Okay? I have to do a little bit of convince you of this, but in fact that is exactly what case 3 of the master method says. Case 3 exactly says the work is dominated at the leaves. All right? And I'll make that concrete. I'll make that precise. Okay. So let's really nail it. Okay, so everything I just told you is true. Okay, that is fundamentally why there are the 3 cases. It's because there are 2 forces at work governing the running time, depending on if it's a draw, or whether it's subproblem proliferation which dominates, or whether it's work shrinkage per subproblem that dominates. You get these 3 cases. Corresponds to work being the same at every level, going up every level, or going down every level, in which case either all the levels are the same, or the root dominates, or the leaves dominates. Okay? We've got about 10 minutes, so let me just really make that vigorous. Finish the proof.